I'm a GStreamer hacker I've been like doing a lot of GStreamer work for a while. Some of you may know me as the maintainer of the V4L elements, but I also do a lot of other stuff around it. My main interest is getting very low level pipeline to work. So to get things like without Wayland, without X, that's really my main interest these days, my main focus. Um, Today, I'd like to talk to you about. It's to me, it's the most recurrent task actually when doing GStreamer development. It's to get the zero copy pipeline to work again. Uh, Hardware vendors are very creative in finding a new ways to get the hardware not to work together, or that adding things that you need to negotiate and to make it convenient. So it becomes like quite a burden, and every once in a while you end up spending half of your year actually fixing yet another zero copy pipeline. So I'd like to share a bit my experience and my knowledge around doing that, so people get ready for their own work. We'll go over what does it mean. I'll try to propose my own definition of zero copy for GStreamer. Then we'll ask ourselves, why do we copy and why should we copy? Because in some cases you should implement the copy. It's actually mandatory for certain cases. And finally, what are the side effects? What will you get if you get it wrong? How do you fix it? What's the mechanism that will help you do that in GStreamer? So, what's zero copy? So, um, I'm not really a dictionary writer. I just created that definition from my own. So I just said that two elements are doing zero copy when the data produced by one element is being used by the other element without requiring an idempotent transform. I search a lot for that word, but what does it mean is basically that you're doing zero copy when you can actually use an incoming buffer directly without having to do a transformation that does not that is not part of your pipeline. That is not something that you need to do. It's like you're doing a transformation, but you're not changing anything. You're just doing transformation to adapt to make it work, basically. So that would be if you can avoid this, you actually reach the zero copy, and you actually stop wasting some of that. So GStreamer actually has a collection of tools that you can use, and the way to use it is really a case by case, because every platform has a little thing that make it different. So in GStreamer, what we have is the ability to wrap your memory, to propose your memory to an allocator, which is basically an interface to allocate memory, just like malloc, but you could do something special in the back. You have the ability to share a pool of memory using buffer pools. All the buffers in memory are ref counted. So that's important in zero copy because you're going to have to allocate memory, and you're going to give that memory to another element. And at some point, you need to track the lifetime of that memory. So ref count is quite a key here. Just a malloc, you don't get anything. You don't if you just malloc and free randomly, it would be really hard to manage. There's the allocation query, which is a mechanism to negotiate various aspects of the allocation. Another very important one is memory logical grouping. So you have the ability to take part of memories and combine them together into a GST buffer. GST buffer is a container for memories, and to actually form a representation of data. That is used in as an example in payloaders. So instead of allocating a big buffer and copying your payload, copying your headers, you can actually just create a small memory, put the payload there, and then in the GST buffer, you put that memory, you put the payload together, and it's virtually combined into a GST buffer. So you keep the array of memory pointers, if you could call it like this, but you don't copy into it. So that's a very important mechanism. And when nothing fits anymore, like you have something that is so different that you just can't do it anymore, it's no longer something that is representable on the CPU, as an example. There's no way to get the memory. There's the caps feature that was added in 1.2 that can be used. Now, how is that used? This is a general overview of how we do the allocation, whether it's upstream or downstream allocation. So the story of an allocation starts mostly by doing like caps queries. I'm simplifying here. There's other steps, but let's say caps queries. Then upstream. Okay, in GStreamer upstream decides. So you'll always see decision being made on the left. So you query your caps, you make a decision, you send your caps. Why the caps matter for allocation? Well, it defines the type of stream you're going to use, and it already contains a lot of information. Like for video, it tells you the width and the height of the video. It tells you the pixel format, so you can already know a lot about your allocation from the caps. The next step, you use that caps actually that you wrap into an allocation query, and then you ask downstream to fill that up with everything he knows about allocation, everything he requires. And upstream, we read this information, and that's actually the most complex part. Actually, it's to try and implement a decision that is the optimal allocation for the exchange between the upstream and downstream. That's often where things go wrong in general in the allocation decision. And when you're ready, then you start producing buffer and you push them. And if you've done it right, it should be able, I mean, the downstream should be able to use your buffers. So that's the mechanism we have in place in GStreamer. As you see, it's not like, it's not telling you everything. It's giving you tools, and then it's up to you to be creative and find what fits for your use case, for your elements, for your hardware, for your software abstraction. It really depends. So that brings me to the second step, the why do we copy? Because you've been around, and there's a lot of stuff that works on your computer by copying all the time, and it's not always invalid. Sometimes it's a good way to actually get going, make it work. So natively, especially when you're sharing your drivers, these are the concept that makes you copy. So the allocation type. Some driver will require memory to be contiguous into physical memory, something that user space is not even able to figure out because everything seems contiguous from user space, but it's in a virtualized table. It could be blocks taken from left and right. Other drivers are more flexible. They will accept scatter-gather, but not virtual memory yet. They don't tolerate any type of caching around that memory. The driver will totally support a virtual memory, and they will have a mechanism to wait for the cache. So the cache is basically when you use virtual memory from the CPU, you write into memory that is on the CPU, and eventually it ends up in RAM. So when you want to take that memory and send it over a wire, over a bus, over a DMA transfer, well, you need that memory to be written into the real memory, because otherwise, when you do the transfer, you'll get an older version of that memory. If you're curious and you have sometimes, you take your USB camera right now, you create a pipeline V4L source to KMS sync, and just move around in your camera, and you'll see there's a bunch of artifacts because V4L have done the caching management wrong, and then we're working on it. So we didn't know before because nobody was doing ZeroCopy to display. There was always an indirection with the GPU. And another type of memory that could happen, and this is very special, could be on a GPU. It could be like a memory on a remote card. So you don't really have access to that memory, but still you're allocating it. So you need to represent it. That's a usual candidate for anything that represents caps feature, basically, because pulling that memory might be impossible or it might be extremely slow. So that's really cool, but the real stuff is that you don't get to see that from user space. You get to see gems, surface, and how many surfaces types that exist out there. I mean, it's an infinite thing. You'll get a DMA buff, but it doesn't tell you anything about what you just seen before. So the truth is that in GStreamer, we're just unable to make a wise decision. We don't have this information. So the reality is that most of the time you'll end up doing like trial and error. You'll try it. So you'll need to allocate a little bit of memory, and you need to ask your driver, can you use that? Like try and use that, and the driver will say yes or no, and then you'll try another bit, and then you'll. So that's also where the decide thing becomes really complex, because you need to activate buffer pools, grab a buffer pool, try that memory, yeah, free that out, allocate more memory. So you may do a couple of allocations, which can be fairly slow, before you actually get it right. So that's something that we'll need eventually to push forward on kernel APIs, on user space, because they don't give us the information to make a wise decision. So just if you're doing it, just get prepared. You might need to trial and error. Another reason we copy, and it's actually a good one. Let's say we have a YUV frame here. It's a quick representation of a planar. Actually, it's looked like a I-420. Doesn't look exactly half, but anyway. So different drivers, different software implementation will have optimizations that requires to index the memory in a multiple of n bytes, usually a power of 2. And this creates require to have a stride or a pitch, you can call it the way you want, that get longer than your width, in fact, if you calculate it. And this requirement might vary between hardware, and you need to find the longest. You need to use the longest stride, which is always a multiple of power of 2 in practice, in order to get a buffer actually that works. Yeah. And then you also need to pass all the metadata. As an example, some driver will have different allocation for each plane. Some driver will want to have a little padding here so they can store some information about the frame. They have their own metadata, like encoders do that. VP8 encoders on Qualcomm 410C is doing that. So they have a little offset over here. So you need to get that right in order to satisfy. And when you can't do that, well, a copy can fix it. You can always copy from one to the other. You copy the blue parts actually to the other buffer, because it's the same width and height. It's the same buffer. There's no transform, but it's just different parameters. Whoops, wrong way. And then there's the story about audio. So there's not much in GStreamer to do zero copy audio. In fact, we don't do that right now. It's much lower bit rate, for now at least, and it hasn't been a problem. But in audio, we'll do, well, that's not really valid because that's not idempotent. But we do format and sampling conversion all the time. But the main reason why we copy in audio is because we use an unified channel order. So everything that travels in GStreamer has all. So in audio, the channels are and the type of audio we support in GStreamer as interleaved audio. So you have like left, right, and then when you have more, 4, 5, 6, 10 channels, we use some standard to put them in a certain order. And this is unified. So if you have a source that has different channel order, you're actually copying in order to reorder these things into the ring buffer before using it in GStreamer. So that's one of the reasons we copy. The other reason it's, and we'll get deeper into that, is because of ring buffers and the way they work, and the fact that it's really hard because if you want to share buffers in a ring buffers, you have a contract. You have a contract to give them back steadily and to give them back in an ordered fashion. And that's extremely hard to do actually with a multi-threaded environment like GStreamer. Just think about adding a T and then it gets complicated. I found it really funny the other day that I just came across that API that I'd never seen before. Probably one of the numerous attempts to do zero copy or to wrap a ring buffer into a buffer pool. if you look at the acquire buffer function, there's a buffer pool allocation params. And you know, there's these leftover that are unused right now. The format, start and stop, which kind of look like what you would need, maybe. I don't know. I really don't have a clear idea about that, but it looks like an attempt to try and get something in. I mean, if somebody wants to look at it and wants to find a way to use these parameters and a way that works, that will be really cool. But yeah. Obviously, you need to know what you're doing when you use a buffer pool that would wrap a ring buffer. There's a contract. You need to return those buffer in the same order, and you need to return them steadily. Whoops. Now, okay, that's great, but I want zero copy. So why would I care implementing copies? Like, why do I do that? Well, the fact is that if you don't implement the copies, your zero copy pipeline will be unusable with any third-party elements that is not compatible in terms of memory layout, memory alignment, memory type. So just to support more interaction, especially because you need not to think your element as something that will always be used in 4K. Some people will do very small, teeny little video, and they're fine with having a copy of that. So if you want your software to be generic and usable and friendly, you could implement a copy. It's also useful for testing. Whenever you want to record the frame to disk, it's nice if you don't have extra padding or stuff, and you can actually make a copy to and analyze the frames in an external tool. And there's also, and we'll get to that later, there's also sometimes it's absolutely needed to be able to at least clone your memory in order to be able to transitions from I would say one format to the other, but the typical use case is to transitions from one resolution to another. So and we'll actually talk about the side effects, and through that I'll get further actually in what I mean by that. So the side effects. To understand the side effects, so what happens when you actually reach the zero copy states, I just created a small pipeline. It's not the usual annotation, but I think it does the job. Because I worked on the T this year to be able to use the T in a zero copy fashion, I decided to put a T over there. So what's new in the T? I think Tim mentioned most of it. So basically, it handles the allocation query. It handles actually the buffer requirements. So let's see. We have here a source, a T, a display, and an encoder. So the encoder will need a couple of buffers to do this, to retain a couple of buffers to actually do his encoding. The display will retain absolutely one buffer because it's a truly, yeah, closer? Okay, sorry. So it's a truly zero copy display. So the buffer that you've given to your display, it's the actual frame buffer. There's no other memory. So it's being hooked to your display and scan out. If you remove that buffer, it will crash. Basically, it won't work. You need something there. So you have two choices: you turn off the display, or you keep that buffer out there. And for the encoder, it's just a backlog. In this case, you see that it's upstream allocation. A little teeny little fact about the T implementation is that it only allows for upstream allocation. The reason is that most people using the T will do dynamic actually pipeline. They will transform actually the downstream branches. And if your allocation was in one of the downstream branches, and then you switch, you end up actually being using some allocators and some buffer pools from a dead object. And for certain stack, that's just not possible. You need to keep the object alive, and then you end up leaking a lot of memory and a lot of context, especially if you have like an encoder. Well, the encoder have a limit, especially a hardware encoder have limited amount of context. So there's limited amount of encoders that can run in parallel. So if you were to allocate from the encoder and then you replace that encoder with another, well, you lost for until the source decide to change to get rid of the allocate the pool. You lost actually that encoder instance. So that's an example side effect. The other side effect is that if the source didn't allocate enough buffers, let's say we only allocated one here, the encoders need at least two. We're pushing one buffer. Display is fine. Encoder is fine. And that's it. I have no more buffer. So pipeline stalled. That's the most common thing that happens when you get things wrong. It's you didn't allocate enough buffers. You have a special allocator that have a limited amount of memory, and nothing's moved. It's not very verbose. It's just it stalls. Your pipeline is dead. Let's move. I'll do a little back and forth with the two slides. So, um, on top of that, many legacy, I call them legacy APIs, but they have a good reason to do things like that. It's mostly designed toward wrapping drivers that implement contiguous memory. Contiguous memory is like the gold memory. It's like very rare. You need to protect it. And if you run out of contiguous memory, your system is pretty much dead. You're not able to allocate memory to actually initialize a frame buffer, not a frame buffer, a firmware. You're unable to do like small allocation that would be required for certain important tasks. So that's why over time, APIs like V4L and OMX put that rule that if you want to allocate a new set of buffer for your pool, you need to discard the old one. And to do this, it forced us actually to implement what we call buffer reclaiming. And what we did in the last 2 years, I think, is about it. We started using the allocation or the drain query to actually implement a proper buffer reclaiming mechanism. So basically, the new contract is that downstream elements retaining buffers, we need to return them back if they see an allocation query coming. Now, if I come back to my previous slide, it's very difficult for the display to return that back because it's my scan-out buffer. I cannot, it's impossible. So what we end up doing is that in those display elements, we detect if the buffer is from upstream. Eventually, we'll need better signaling. So we'll be able to signal on the buffer that this buffer need to be reclaimed, and this buffer can be kept. But right now, what to do, we make a copy into proper memory. We render a new buffer, and then we discard the old one. That's what we do currently in KMS Sync. It's not ideal, it's slow, but at least it doesn't break. So you can switch resolution. Now that's it. That's great. All the problems I mentioned is nice. But what do you gain? Well, when you get that right, you get high performance, you get more CPU time for your UI guy to create a nice UI. You get lower processing latency, so it's mean that you get smoother rendering. You get more time to schedule your frame on the screen or on your audio card, and you're less likely to get glitches because you have so much like time ahead of you for your rendering. That's really what you're looking for. So what for the future, what I would really be interested in seeing, and that's why I want to speak with Marcin, is having tools in GStreamer to actually monitor the effect of my ZeroCopy pipeline to look at the health of that ZeroCopy pipeline to make sure that yes, I'm using much lower CPU. I'm not allocating too much. My latency is going down because it's right and things like that. It's really hard right now to visualize this in GStreamer, and I'm really looking forward to creating and contributing to tools that will help doing that. I think we can take a couple of minutes for questions if you guys are interested. Any questions? Yes. I'll repeat. I'll repeat the question. Okay. So caps feature, as I said, it's when nothing of the. Oh yeah. So the question is basically, and correct me, is how does it work? Uh, how does it work between an element that is not aware of a caps feature with a downstream element that implements a caps feature? And what you need to be aware is that it's last resort to use a caps feature. And when you use a caps feature, it's up to that stack to implement the transitioning element. I'll take an example. GL caps feature. So GL memory. In GL memory, we have GL upload and GL download. If you want to exchange generically with that, you need to use GL upload or GL download in order to interface with that new world. Because as soon as you pick caps feature, it's your own rules. You're redesigning the thing from scratch. Everything that is going to happen is defined by you. There's nothing related to system memory that will apply in your case. It's a new set of rules. The negotiation, the assumptions, the contract between two elements. As soon as you pick you need to know that you're on your own. So to make that work, you need the transitioning element, and then unfortunately, you need also specialized code that will place those elements in order to upload and download. In GL, we have actually GL image sync. It's secretly a bin, and it had a chains of elements in order to transform your memory to GL. Maybe one other question, or are we good? So myself, I never work on TX1. Oh yeah. So I'm asking if I worked on NVIDIA platform and TX1. I never work on anything newer than Tegra 3. Um, but I do help people with Tegra 3 pipeline, ZeroCopy pipeline these days. Um, I think right now the big mistake, I have access to some property code and headers, and there's some of those headers that should have been considered system headers, and that should have been publicized in order to make it possible, basically. Currently, NVIDIA hides their own memory allocators. They have a nice, actually, it's very good memory allocator, but it's very usable. There's all the mechanism to transitions from system memory to their GPU memory and stuff, but that header is still considered like if you paid, you have access to it. If you don't pay, you don't have access to it. And it means that we're not allowed to write GPL code around it. We're not allowed to include that in GST-OMX as an example. So there's a problem there. Somebody will need to work with them. The problem with NVIDIA is not the devs. They're very kind, they're very helpful, but they have a big legal department, and it takes years to actually figure out things. So I hope it's going to improve, and they're not doing it this way to make your life bad. They're doing their best, but it's a company setup that prevents from doing proper open source in this case. And from my experience, there was this one header. If it was made public, it's just a header. It would make a hell lot of difference, because to me, I mean, they have a whole new system. It's not Linux. It's some like portable interface on Tegra, and to me, this is the OS. This is their own OS. It's the NVIDIA OS, and if you don't expose the headers to use the OS, it's not an open. It's not an open system anymore. It's not like Windows and Linux and OS X and all the others. So it's not equal. So I think the day they open those headers, we'll be able to do things properly. So I think that's it. We have no more time. Thank you very much. And if you have more questions during the day, during the conference, just come by. I'll be very happy to answer.